Welcome everyone to this 14th episode of my publication at a glance. Today we have the pleasure to welcome Dr. Lucie de Cremoux, who did her PhD at the University Paul Sabatier in Toulouse and at the CNRS. And will talk to us today about Alzheimer's disease and amyloid plaques. Lucie, the floor is yours.
Thank you for this kind presentation and for giving me the opportunity to present my work on the modulation of A-beta 140 and A-beta 440 co-assembly by zinc in order to get in closer to the biological reality. So I'm working on the field of the Alzheimer's disease, which is, as you all know, the most common neurodegenerative disorder, and for which we have no curative treatment for now. And this disease has three neurohistopathological hallmarks, and I'm just going to talk about the amyloid plaques. So the amyloid plaques are constituted here of amyloid beta peptides, and it's a broad family of peptides with different forms of the peptide. So today I'm going to talk about the A-beta 140 peptide and A-beta 440 peptide, which are the two most abundant A-beta peptide forms. Here we have the sequences of both peptides, and I'm going to talk about the A-beta 140 from 1 to 40 amino acids, and which is the full-length one, and the A-beta 440. The main difference between these two is the loss of the three first amino acids on the A-beta 440 peptide. As I said, the amyloid plaques are constituted of amyloid beta peptides, but also of metal ions, such as copper and zinc at high concentrations. It was detected that they were coordinated with A-beta peptides and which could lead to deleterious impacts. Moreover, due to this coordination, they are able to modulate A-beta cell assemblies and the morphology of the fibrils. The way to study the metal ions impact on A-beta peptides is to study one metal ion with one peptide at a time. The idea of this paper is to evaluate metal ions coordination and impact with A-beta peptides in more biological relevant conditions to better mimic the synaptic cleft media. So the idea is to involve three partners at a time. So here, one metal ion and two peptides to better mimic the synaptic cleft. Similar studies were only reported once in the literature with copper-2 ions, so the idea now is to realize this kind of studies with zinc ions. The main point was first to know the coordination site of zinc metal ions within both peptides, and it was already published for the full-length one. So with XAS and NMR experiments, and based on the literature with the results obtained on A-beta 140, we could propose these two coordination sites with a pKa around 7.4. And something which is quite interesting is that we have similar coordination sites between the full-length one and A-beta 440 with implications of imidazoles and carboxylates. We also performed affinity tests, and we could see that the affinity for A-beta 440 is 4 times lower than the full-length one, so it could imply different modification of the self-assembly process. So we realized the self-assembly process monitored by the thioflavin T, and here are the results for A-beta 140, where we have the classical sigmoid curve. And the first part of this sigmoid is the nucleation, where we have an organization of the monomers of the peptide to form nuclei. And then we have the elongation step, where we have the addition of the monomers on the nuclei to form fibrils. At the end of the process, we could observe the fibrils by electron microscopy, and we can see something which is quite interesting here, is that we have twisted fibrils. We also performed these assays with A-beta 440 peptide, and we could see that the nucleation step is quite faster. So the formation of nuclei is faster with A-beta 440 peptides, and at the end of the process, we obtain different fibrils. The equimolar mix of both peptides was also realized, and at the end of the process, we obtained different fibrils. So we have something in between the two self-assembly processes, and not from one part the A-beta 140 process and the A-beta 440 process in the other part. So we can propose this kind of mechanisms where we have the formation of A-beta 440 nuclei faster than A-beta 140, and then we have the addition of both monomers from both peptides to form hybrid fibrils. We also realized this kind of experiments with zinc metal ions at different concentrations, but I can show you the results at 0.5 equivalent. And something which is important is to see that we have a different self-assembly modification by zinc metal ions on A beta 140 and A beta 440 peptide here in blue and green, and the obtention of different kind of morphology from the fibrils. For the equimolar mix, we have also something which is in between, so not the interaction of zinc on A beta 440 and A beta 140 separately, but something which is quite the interaction between the two, and we obtain also different fibrils morphology. So the mechanism is really complex, so I let you observe and read the paper if you are interested on these mechanisms. So the idea of studying the co-assembly of two peptides and one metal allow better comprehension of the complex mechanisms occurring in the synaptic cleft. And with this better comprehension of these mechanisms, we can have a better understanding of the mechanisms of Alzheimer's disease and maybe a way to find new therapeutical strategies.
Thanks a lot, Lucie, for this very clear and interesting presentation. I would encourage anyone interested to go check your paper. If anyone also wants to present the latest result, please do not hesitate to contact us. You have everything you need on that slide. Thank you and see you next time.